Hello again, my friends. How are you doing today? Alright, so I promised you to do another video to calculate the capacitance of a cylindrical capacitor. So here I brought an example, and the example says, consider a solid cylindrical conductor of radius A surrounded by a coaxial cylindrical shell of inner radius B. The length of both cylinders is L, and we take this length to be much longer than B minus A. That is this large radius minus the small radius. The separation of the cylinders so that the edge effects can be neglected. That means if it's too long, then the edge effects will be neglected, as I explained that in the previous video. The capacitor is charged so that the inner cylinder has charge positive Q, that is this one here, and the outer shell has a charge negative Q. What is the capacitance? So, before we solve this problem, we have to do 3 steps. And those 3 steps is that first, we need to find the electric field using Gauss's law. The second step is we are going to use E to find the potential difference between the 2 shells. And step 3 is to find the capacitance using the definition, that is the charge placed on the capacitor over the difference potential between the 2 shells. And that is the voltage that pushes charge to the plate in the previous problem as I explained it. So how do we start? First of all, we need to use Gauss's law, and that is we have to choose an arbitrary R, a Gaussian surface. We know that if we choose the Gaussian surface to be inside this conductor, then the charge will be 0 because the charge will reside on the surface of the conductor, that is outside of the conductor. So the positive charge would be outside of the conductor, and inside the charge will be 0. So we cannot place we cannot choose the Gaussian surface to be inside the small cylinder. And if we choose the Gaussian surface to be outside of the cylinder, then because we know that the smaller cylinder has a positive charge and this one has a negative charge, which is the large cylinder has a negative charge, they're equal in charges but opposite, then they will cancel out and the charge will be 0. So the only way left is we choose R to be between B and A, and that is here is a small r. Okay. Now we are gonna say that L, small l, we're gonna choose a small l, and that is gonna be less than large L. So L is less than big L. Okay. We can see that the electric field of this conductor here, which is the smaller radius, is pointing away because it's positive. Okay. So now let's calculate the electric field using Gauss's law, and that is, let me change the color, let's use black here. So the surface integral of E dA is equal to E A, and that is equal to E times 2 pi R L equal to Q enclosed, and this one is equal to Q enclosed over epsilon naught, and we know that Q enclosed of the Gaussian surface is equal to lambda small l over epsilon naught. We know that the L and L cancel out, and we will be left with E equal to lambda over 2 pi epsilon naught small r. So that is step one. It's done. Now, we need to calculate the potential difference between the two shells. And that is going to be V equal to the integral of dV. That is always the case. Then we're going to say dV is equal to negative E dr, and dV over dr is equal to negative E. This is basically standard electromagnetic equations. Now V is equal to, we're going to substitute now negative. We're going to take the integral from small a to b. So from a to b of E dr. Okay. Then what we're going to do is that the negative, we're going to substitute E with what we found in step one here. So a to b of lambda 2 pi epsilon naught times r times dr. Okay, that is going to give us. So what we're going to do to get rid of this negative here, we're going to switch the limits. Okay, so the negative will go out and we will take all the constants outside of the integral. So the constant we have lambda over 2 pi epsilon of naught. As we said, we're going to change the integrals from b to a. And then we have 1 over r dr. Okay? Now, this is going to equal to lambda 2 pi epsilon of naught times the natural log of a minus the natural log of b. And because of the natural log rule, we can write this as lambda over 2 pi epsilon of naught natural log of a over b. So that is step 2. Now step 3, which we need to find the capacitance of the capacitor, and that is equal to, we know that C is equal to Q over V, delta V, and we know that Q, as we said earlier, is equal to lambda times L. So lambda times L over delta V, which we found here, that is lambda times 2 pi epsilon of naught times natural log of a over b. Lambda and lambda cancel out, and we left with this gonna go up, and this is gonna be 2 pi L epsilon of naught over natural log of a over b. That is the capacitance of cylindrical shells. And then, so let's recap what we did here. So those are the 3 steps again. We found the electric field using Gauss's law. That is this one here, EDA equal to EA equal Q enclosed over epsilon, which is equal to E 2 pi RL and equal to lambda L over epsilon. And we found E. That is step 1. Then step 2, we used E to find delta V, that is the potential difference between the two shells, using V equal dV and dV equal negative E dr and dV over dr equal negative E, and we substituted and we found the difference potential. Then, third step, we use the capacitance equation to find the capacitance on the cylinders. Alright, so next video I will explain the spherical capacitors, and see you then.